Okay, so today we're going to talk about a piece of technology that could totally change how we think about our data. It's called homomorphic encryption, and honestly, it's a way to compute on secrets, which sounds a lot like magic. And in the world of cryptography, it's about as close as you can get. And look, this isn't just some abstract idea from a computer science textbook. It's a real solution to a massive problem we all deal with every single day. I mean, think about it. We love the cloud, right? We use it for everything, storing our photos, running our businesses. But to do that, we have to hand over our private data to somebody else's servers. And that leads to this huge question. Is it even possible to use the cloud without just giving away our privacy? So here's what we're going to cover. First, we'll dig into that cloud privacy problem. Then we'll get into the cryptographic magic trick itself. We'll look at the incredible 30-year journey to get here, talk about a big challenge called noise, see how researchers are building better encryption today, and finally, look at what's next for all of our privacy. Okay, let's dive right in. We're starting with the big one, the core dilemma of our modern digital lives. So let's talk about how encryption usually works, right? You've got your data, we'll call it plain text, and you use a key to scramble it up into something called ciphertext. And that's great. It's secure while it's being sent over the internet or just sitting on a server. But, and this is the huge but, for a cloud server to actually do anything with that data, like run a simple calculation, it has to unlock it first. It has to decrypt it. And in that one moment, your private data is totally exposed. That's the vulnerability, the trade-off we've all just kind of accepted for years. So that begs the question, how on earth can you compute on data that you can't even see? Well, this is where things get really interesting. This is the part that sounds like it should be impossible. This is where homomorphic encryption, or HE for short, just completely flips the script. It's a type of encryption that lets a computer perform calculations directly on the encrypted data. You heard that right. The server can add numbers, multiply them, do all sorts of processing on your scrambled up ciphertext, and the result it gets back is still encrypted. The server never needs your key. Your data is never exposed. It's a total game changer. Okay, I know that sounds pretty abstract. So to make this crystal clear, let's use a brilliant analogy from Craig Gentry, who's basically one of the fathers of this field. Imagine you've got a jewelry store owner, we'll call her Alice, and Alice wants her employees to assemble some super valuable jewelry, but she's worried, that they might just pocket the gold and diamonds. So what does she do? She comes up with this amazing special lockbox. Step 1. Alice puts all the raw materials, the gold, the diamonds, into the box and locks it. That's our encryption. Step 2. The box has these gloves built right into the side so the workers can put their hands in and assemble the jewelry without ever directly touching the materials. They are computing on the secret stuff inside. And finally, step 3, they give the locked box back to Alice. She's the only one with the key. She unlocks it and takes out the finished necklace. That is a perfect picture of how homomorphic encryption works. Now, this whole idea might sound super futuristic, like something out of a sci-fi movie. But believe it or not, the concept has been around for decades. The journey to actually make it work, though, well, that was a really long one. That's why people in the field have been calling it the holy grail of cryptography for a very, very long time. So get this, the core idea, called a privacy homomorphism, was first talked about all the way back in 1978. But for more than 30 years, it was just that, an idea, a theory. The huge roadblock was figuring out how to create a system that could handle all kinds of math, specifically both addition and multiplication, which is what you need for it to be fully homomorphic. For 3 decades, the math was just mind-bogglingly complex, and frankly, the computers we had just weren't powerful enough to pull it off. And then, in 2009, everything changed. Craig Gentry, yep, the same guy with the jewelry box story, published his PhD thesis. And in it, he laid out the very first plausible scheme for fully homomorphic encryption. This was it. This was the moment that turned a theoretical dream into a practical reality. It kicked off a massive wave of research and innovation that's, still accelerating today. Okay, so if Gentry gave us the blueprint back in 2009, why isn't this everywhere yet? What makes it so incredibly difficult to use in the real world? Well, it pretty much all boils down to one single critical challenge. Something called noise. Here's how it works. To make the encryption secure, you have to add a little bit of random mathematical noise to the data. It's like adding static. That's what makes it so hard for an attacker to crack. But here's the tricky part. Every single time you perform a calculation on the encrypted data, every time that worker uses the gloves on the box, it adds a tiny bit more noise to the mix. And, well, you can see where this is going. If you only do a few calculations, it's fine. The noise is low, and Alice can still decrypt the result and get her beautiful necklace. But if you do too many computations, that noise starts to build up and up and up until it completely overwhelms the original data. The final result is just gibberish. You can't decrypt it correctly. So managing this noise problem, that is the absolute central challenge in making this technology fast and practical for everyday use. And that brings us right up to the present day, to the cutting edge of research, where computer scientists are working hard to build newer, better, more efficient ways to handle all that noise. And a perfect example of this is a recent master's thesis by Nala Yehe. What she did was take a brand new, highly efficient FHE scheme, one that was only proposed a few years ago by researchers Dawara and Krishnaswamy, and she actually built it. She implemented it. So what makes a new scheme like this one better? Well, a lot of the older popular schemes have this one annoying problem. Every time you do a multiplication, the encrypted data, the ciphertext, actually gets bigger. This forces you to do this really slow, expensive cleanup step called relinearization to shrink it back down. But the new scheme that Yehe worked on, it cleverly avoids that whole problem. The ciphertext size stays stable, which makes multiplication way, way more efficient. Her work is a really big deal for a couple of reasons. First off, it's the very first time anyone has actually implemented this new scheme, proving it works in practice. And second, she started exploring how to extend it to a multi-key setting. Now that is super cool. It means you could have different people or different companies, each with their own secret key, all working together on the same encrypted data without ever having to share their keys with each other. Think about the possibilities there. So all of this deep, technical research, it's all building towards a future that could look radically different, with some absolutely transformative possibilities. Yeah, this is not just some theoretical exercise for computer scientists. We're talking about real-world applications. Imagine training an AI on sensitive medical records to find new cures for diseases, but without ever exposing a single patient's private information. Or imagine being able to search your cloud photos for beach without the service provider ever knowing what you searched for or what's in your photos. This is the technology that could finally give us a truly secure and private cloud. You know, for basically my entire life, the internet has been built on this one fundamental trade-off. You get amazing services, but you have to give up your privacy. Homomorphic encryption holds the promise of a future where we might not have to make that choice anymore. A future where utility and privacy aren't opposites. So that leaves us with one final, massive question. If our data can stay completely private and be completely useful at the same time, what are the next big problems we can finally go out and solve?